Today, I'm going to show you the 3 ways that you have to know for evaluating a line integral. And the line integrals that we are focusing on today, they will look like this. And in fact, they are called the factor line integrals. You have the dx and dy. That's how you can kind of look at it. The other kind of integral is called the scalar line integrals, and they have the ds at the end. Those integrals, you pretty much only have parametrization to do them. I will show you guys other examples on that later, but for these right here, you have to know these 3 ways. For the first one right here, we're integrating over the curve c, and c is defined to be the factor t and e to the t. So if you look at it, just imagine we have x, and this is just e to the x. So we're looking at the equation y is equal to e to the x, so it's that curve. First thing first, this is not a closed curve because it's just a piece of the curve, right? So definitely not the Green's theorem. Definitely not. The Green's theorem, well, the first criteria is it has to be a closed curve, right? The other thing that you have to know is that, think about, can you have a function, differentiate that with respect to x, you get this, and differentiate that with respect to y, you get that. If that's the case, then you can use the fundamental theorem of line integral. That will tell you, you cannot do that either. So for the first one right here, we'll just do the traditional way, and that is the parametrization. So x is t and y is e to the t, and then just do the work. This right here will be the integral to x is t, and then y is e to the t, and then we have to square that. dx, you look at this and differentiate that, you get dt. Continue. X is the same as t, square that. Y is e to the t. Now dy, be really careful with this. Y is e to the t, so dy is equal to, you take the derivative of this, which is e to the t, and then dt. So e to the t dt. And of course, you can cancel this out. And now notice, both of them have dt, so you can put that all the way at the end. And that's it, we're in the t world. T goes from 0 to 1. So just go ahead, plug in 0 and 1 right here. And we can clean this up a little bit. We will have 2t, and they are out already, so plus t squared and dt. And of course, you can just integrate the first, integrate the second, and then work it out. That's it. For the first one, we will have to use integration by parts. So let's do it real quick. And I can get 0, so I will differentiate 2t, and then I will integrate e to the 2t. Differentiate this 1 time, 2 times, I get 0. Integrate this, we get e to the 2t. Don't forget to divide it by the 2. Do it again. Divide the 2 one more time, we get 1 over 4. So we get this times this times that. So we will have this times that, 2 cancel, so it's t e to the 2t, and then minus 1/2, and then e to the 2t. So that's for this part. And then integrating this is of course just 1/3 t to the 3rd power, and we go from 0 to 1. Okay, when we plug in 1, we get e squared minus 1/2 e squared, and then plus 1/3. So that's the first part, and then minus, plugging 0, that's out, but that's a minus 1/2, and then 0, so that's what we have. And then finally just work that out. That's 1/2 e squared, and then 1/3 plus 1/2, you get 5 over 6. So parametrization, that's the first way. Now for the second one, this is the curve. Do we really want to plug in cosine t into all the x's, e to the 2t into all the y's, and then integrate all that? Let alone the dx, dy, also have to differentiate all that stuff. I don't think so, it's too hard. Definitely don't do that. Maybe you can do it and then work that out perfectly if you want to go for that, go for that. But I want to tell you guys two other ways. We mentioned this earlier. Let's talk about green theorem first. If you want to use green theorem, one of the first things that you should check is this a closed curve? Meaning if you plug in the beginning t value into here, do we end up with the same value when you plug in the n value into the t? Okay, when you plug in 0 into t, cosine t is 1, but when you plug in pi, you get -1. For sure it's not closed. So say bye-bye to the green theorem. Now, the last way is the fundamental theorem of line integrals. What I mean is the following. Remember good old Calc 1, if you have an integral, the regular one, if you happen to integrate a derivative, this is super nice because the integral and derivative cancel. You just get the function, and then you just have to plug in b and then subtract plugging a. Well, same idea here, but this we're just dealing with a multivariable function. The idea is that can we find a function f comma xy such that if we take the partial of this with respect to x, and we get this right here. And then in the meantime, if we take the partial with respect to y, we get this right here. And for the people who have done some differential equations, yes, this is exactly the same idea of solving a exact differential equation. If we can do this, it will be super nice because again, it's just going to be like the integral and the derivative cancel. So how do we know though? For the first example, I just told you it was not possible. For this one, let me show you how to check. The key right here is that you have to remember mixed partials are equal if the function is nice enough. So when we have this, let's take the derivative with respect to y. In that case, what do we get? That's out because x is a constant in the y world. Take the derivative of this, we get 6y squared. And then we take the partial with respect to x. Remember, we do the mixed partial. Okay, this is out, and the derivative of x to the first power is just 1, so we get 6y squared. They are equal, so that means it is possible to have a function that will make this work. Now, how do we find out such a function though? Okay, let's begin with this idea. You can start with either one. If you have a function which the partial derivative is equal to 2x plus 2y to the third power, let's just go ahead and integrate this with respect to x. In that case, it looks like we have our f. Integrating this, we get x squared. Integrating this in the x world, we get 2xy cubed. But remember, we still have to have a constant. What's the constant though? It's not just plus c, because any function in terms of y is considered a constant in the x world. So I will say plus g of y, like this. And then, this is the general form of our function. Let's have a look. Well, the other piece of the information is this. That's partial f with respect to y. So that means I better look at this and then differentiate this with respect to y. So I can get partial f with respect to y, and that is 0. Put a 3 in the front, minus 1, so 6xy squared, and then plus g prime of y. Now, this should be the same as that. This and that are equal, so that's nice. So that suggests us that g prime of y has to be equal to -1 over y, meaning g of y has to be negative ln of y. Okay? So this right here is the idea, and I don't think we need absolute value because later on we plug in some positive stuff, so we should be okay. So our function is what? We have this and that, x squared plus 2xy cubed, g of y is this, minus ln y. Do I need to put another plus constant? No, we don't. This is it. Maybe there's some number so we don't need to worry about that. Just like when we find an antiderivative of this, you don't need to do any constant, none of that. So now we have our function. Remember, this is just the total differential of this function. When we integrate the differential, well, integral and derivative cancel, we will just get this function back. So use this right here. And remember, we really don't need the plus c because we will do the plugging numbers, and then if you have a plus c, the constant will subtract each other anyway, so it doesn't matter. But what number do we plug in though? Be careful, it's not 0 and pi, because here we are in terms of x and y. So we will have to see when t is equal to 0, which point are we talking about? Cosine 0 is 1, and then e to the 0 is 1. So we are going to start at 1, 1. X is 1, y is 1. And then when t is equal to pi, we get cosine pi is -1, and then e to the 2 pi. So I will have to go up to -1 e to the 2 pi. So here we go. Plugging this into x first, we get +1, and then plugging this into here, we get -2, and then e, and then 3, and then multiply the power, so we get 6 pi. We don't have x here, but if you plug in this right here, ln and e cancel, so it's just minus, and then we just get 2 pi. Okay, so that's the first part. Then we are going to subtract, plugging 1 into all that. 1 into x, we get 1. 1 into this is 2, and then 1, so it's +2. And lastly, that's ln 1, which is 0, so that's what we have. And then we just have to clean this up a little bit. -2 e to the 6 pi all the way in the front, and then -2 pi, that's 3, and then 1 minus 3 is -2. So this right here is the value of that integral. Nice and easy, under the condition that we can find such a function. That's it. Of course, the last one, it has to be the green zero. So let's have a look. Now for this one here, have a look. We have a triangle, which is a closed curve. That means we can possibly use the green zero. But we also have to check the function though to see if it's good or not. Notice there's no x, y on the bottom, so there's no undefined places. We should be pretty good. Later I will show you an example where even we have a closed curve, we cannot use green zero. We have to be careful. But for this one, we can apply the green theorem, and sometimes we put a little circle over the integral sign just to show it's a closed curve. Let's say we have p dx plus q dy. Green theorem says when the vector field is good enough, we can turn that into a double integral over some region D, which is this triangle here. And inside here, this is what we do. We do the q, take the derivative with that, take the derivative of q with respect to, we'll take the partial derivative of q with respect to x. Subtract, take the partial of p with respect to y. So in fact, you will see that we do not have to deal with this part, which is very, very nice. Okay, let's turn this into a double integral. Let's figure out the partial derivative first. This is my q. I will have to take the derivative of this with respect to x, which will just get 2xy. Now, if we look at the p function, take the partial with respect to y. All this is in terms of x. It's just a constant, so it's -0. So nice. Now for dA, it depends on how you want to do it. You can go from left to right first or up and down first, up to you. If you want to go from bottom to top, then you do dy dx. Now, we are in the y world first, we need the bottom function, which is just 0. Up to the top function, well, here we have a line. So it's going to be y equals, we have the origin, so the y-intercept is 0, and the slope is 3 over 2. So it's 3 over 2x. So that's the equation here. So bottom function to the top function, and in terms of x, we go from the left number to the right number, which is 0 to 2. Much better compared to the original one, right? And now we just have to finish it. Let's go ahead, depends on how you want to do it. I'm just going to integrate this right here, which will get x and then y squared, and we will have to plug in 0 and then 3 over 2x into the y. So this will give us integral from 0 to 2, and then x, that's 3 over 2x squared. So that is 9 over 4. It's a constant, so put that outside, and then 0 to 2, and then we have x squared and x cubed. Alright, so we will have, add 1, we get 4 divided by 4 is 16 on the bottom, and x to the 4th power, and we go from 0 to 2. Plug in 2 to the 4th power is 16, and that they cancel, we have 9. Plug in 0, doesn't matter. So the final answer for this is just equal to 9. Green 0.